Imagine this: volcanoes, those mighty mountains of fire, each standing as a silent testament to the Earth's furious power, suddenly seem to awaken all at once. The ground trembles beneath your feet as you hear about eruptions happening simultaneously in regions across the globe, from the fiery heart of the Pacific Ring of Fire to the far-flung volcanic chains in the Atlantic. You can almost feel the heat radiating from the explosions, the fiery magma spilling into the ocean, and the thick plumes of ash blotting out the sun. It's a scene straight out of an apocalyptic movie, and yet, it's happening right before our eyes. But what's even more intriguing is this: these eruptions aren't just happening sporadically or in isolated pockets of the Earth. They seem to be synchronized. As if, in some strange cosmic way, the Earth is aligning its volcanoes into some chaotic choreography. One moment, there's a volcanic eruption in Indonesia, then a day later, there's another one in Iceland, and not long after that, the Earth shakes in Mexico as yet another volcano releases its fury. The synchrony isn't just a coincidence, it's happening with unsettling frequency. To the untrained eye, this may seem like a quirk of nature, a random series of geological events. But to scientists, it's a growing concern. Volcanoes are supposed to erupt on their own time, dictated by the slow-moving and unpredictable processes deep within the Earth's crust. Their eruptions are usually driven by the pressure of magma building up beneath the surface, and the eruptions themselves are the result of localized geological conditions. So, when eruptions start to follow one another across the globe, many scientists are left scratching their heads. Could this just be a statistical fluke? A strange series of events that, once fully analyzed, will turn out to be entirely explainable? Or is there something more profound at play? Perhaps an unseen force, some deep and uncharted natural phenomenon, is stirring the Earth's crust into a new kind of pattern, one that we're only beginning to understand. In the past, we've seen global events that triggered massive shifts in geological activity. Major earthquakes, asteroid impacts, and even the movement of tectonic plates have been linked to clusters of volcanic activity. But what makes this particular situation even more unnerving is the apparent synchronicity. It's as though the volcanoes, each with their own unique, individual triggers, are somehow being influenced by something that spans the globe. Is it a cosmic alignment, a shift in Earth's magnetic fields, or some other phenomenon that we simply haven't discovered yet? What we do know is this: volcanoes have been erupting for millions of years, but the scale and frequency of recent events are unlike anything we've seen before. Scientists are racing to study these eruptions, to understand the complex processes behind them, and to figure out whether they're connected in some way that could threaten entire regions, or the planet itself. For centuries, humans have looked at volcanoes with awe and fear, knowing that beneath their beauty lies an unpredictable, destructive force. But now, as these eruptions seem to be happening in lockstep across the globe, the question has shifted from mere curiosity to real concern. How much longer can we ignore the growing signs of a planet that may be on the brink of a major geological shift? Some researchers argue that there's no need to panic just yet. After all, volcanic activity is not entirely unusual. It's part of the Earth's natural processes. The Earth's crust is constantly moving, and as the tectonic plates shift, volcanoes will erupt. But the more frequent and coordinated these eruptions seem to be, the more uneasy the scientific community becomes. Could it be that we are witnessing the early signs of a larger geological event, something much more catastrophic than anyone anticipated? Or is this just a fleeting pattern that will soon fade away into the pages of history? Whatever the answer, one thing is clear: the world of volcanology is experiencing a shift. What was once a realm of isolated studies and minor eruptions has now turned into a complex puzzle that scientists are eager to solve. The synchronization of these eruptions is a clue, one that could unlock secrets about the Earth's inner workings, or perhaps reveal an unexpected global connection that we've never thought possible. Stay with me as we delve deeper into the strange and mysterious world of volcanoes erupting in sync. The questions we'll explore may not have clear answers right now, but the journey of discovery will be nothing short of thrilling. Before we go into detail, I encourage you to consider subscribing to the channel for more updates on the Earth. Now let's begin. As we dive deeper into this intriguing pattern of synchronized volcanic eruptions, it's essential to understand that there is one prominent theory that has begun to surface with increasing frequency in scientific discussions: the potential role of tectonic plate movements. The Earth's tectonic plates, those colossal slabs of rock that form the outer shell of our planet, are constantly in motion, though their movement is so slow and gradual that we often overlook their profound influence on everything from the stability of continents to the eruption of volcanoes. Imagine, if you will, the Earth's crust as a giant jigsaw puzzle. Each tectonic plate is like a massive piece of that puzzle, and they're all slowly shifting, sliding, and colliding with each other. These plates rest on a layer of semi-molten rock called the mantle, and their movement is driven by forces deep within the Earth's interior. This process is called plate tectonics, and while it's a concept that has been well understood by geologists for decades, its full complexity is still being explored, especially when it comes to volcanic activity. You might wonder, why focus on tectonic plates? What do they have to do with the synchronous eruptions we're seeing? The answer lies in the way tectonic plates interact with each other at their boundaries. When two plates collide, one may be forced beneath the other, a process known as subduction. The plate that is forced downward melts under the immense pressure and heat, and the magma created in this process can rise to the surface, leading to volcanic eruptions. It's in these regions, where plates meet, that the most explosive volcanoes tend to be located. But here's where it gets even more fascinating. The movement of these plates isn't just confined to the areas where volcanoes are currently erupting. In fact, the interconnectedness of plate tectonics means that even distant regions, seemingly far removed from one another, can be influenced by shifts in the tectonic plates. Imagine one plate shifting under the ocean floor in the Pacific and causing a subtle ripple in the overall tectonic balance of the planet. This ripple effect could, over time, cause other volcanic regions to experience pressure buildup, ultimately triggering a cascade of eruptions in other parts of the world. This phenomenon, while still a theory, has begun to catch the attention of researchers. What if these simultaneous eruptions are the result of distant tectonic shifts, rippling through the Earth's crust like a seismic wave? It's an unsettling thought. As the plates shift, the stress created by the tectonic forces could be enough to push dormant volcanoes into action. The way these shifts occur, slowly, gradually, and sometimes over long periods of time, might explain why multiple volcanoes seem to erupt within a short time frame, even if they're located thousands of miles apart. One key piece of evidence supporting this theory lies in the history of volcanic eruptions. If we look at past volcanic events, we often see that large-scale eruptions tend to cluster together in time and space, with specific regions experiencing heightened activity after tectonic shifts. The volcanic eruptions that occurred in the wake of significant earthquakes, for example, often showed a pattern of synchronized activity, as if the energy from the tremors had set off a chain reaction. While these events are difficult to predict, they highlight the profound interconnectedness of geological processes. To further understand the connection between tectonic plate movement and volcanic activity, let's consider the example of the 2011 Tohoku earthquake in Japan. This massive earthquake triggered a series of volcanic eruptions in the region, many of which had been dormant for centuries. The energy from the quake caused the tectonic plates to shift in a way that reignited volcanic activity. It's as if the shaking of the earth beneath the surface set off a chain reaction that was felt far beyond the immediate area of the quake. While this may seem like an isolated case, researchers are beginning to wonder if such events could be more common than we once thought. In fact, the theory suggests that we may be living in a time when the Earth's tectonic activity is reaching a kind of crescendo. Some experts believe that the movement of tectonic plates is accelerating, a phenomenon that could be linked to the shifting balance of forces within the Earth's mantle. As these plates continue to move and collide, the likelihood of multiple volcanic eruptions happening in tandem may increase. This growing sense of urgency among scientists is spurred on by new data that suggests that volcanic activity is indeed becoming more synchronized in recent years. But here's the real kicker. These tectonic shifts aren't just affecting the volcanoes where eruptions are occurring. The ripple effects of these movements may be influencing the stability of volcanoes in areas that are not currently erupting. It's as though the entire planet is one interconnected system, where the forces beneath our feet are quietly pulling the strings, setting off volcanic events in far-flung corners of the world. Could it be that tectonic movements are triggering a global chain of volcanic eruptions, each one linked to the last in ways that we're only beginning to understand? As we continue to monitor volcanic activity across the globe, scientists are focusing more closely on these tectonic shifts as a potential cause for the synchronization of eruptions. The question remains, are these eruptions merely coincidental, or is the planet's tectonic machinery operating in a way that we have yet to fully comprehend? One thing is clear: the Earth's crust is far more dynamic and interconnected than we once realized, and understanding the role of tectonic plate movement is crucial if we are to make sense of the increasingly frequent and synchronized eruptions occurring around the world. As we reflect on the immense scale of tectonic plate movements and their undeniable role in triggering volcanic eruptions, it's important to explore one particular aspect of this theory that adds another layer of complexity to the situation: the concept of plate boundary zones. These zones, where tectonic plates converge, diverge, or slide past one another, are not only where the majority of the Earth's volcanic activity occurs, but they are also areas where the forces of nature are often amplified. It's within these boundary zones that we see the most dramatic and violent eruptions, and where the impact of tectonic shifts is often felt most profoundly. Consider the Ring of Fire, for instance, a horseshoe-shaped area around the Pacific Ocean that's home to about 75% of the world's active volcanoes. This zone is a prime example of the relationship between tectonic plate boundaries and volcanic activity. The Ring of Fire is located at the boundaries of several major tectonic plates, including the Pacific, Indo-Australian, and Eurasian plates, and it's here that the violent interaction between these plates leads to frequent earthquakes, volcanic eruptions, and other geological events. It's important to note that these plate boundaries are not static. They are in a constant state of motion. The plates themselves are drifting at an incredibly slow pace, typically just a few centimeters per year. But over thousands of years, this movement can result in significant shifts in the Earth's surface. These slow, cumulative shifts are not always easily detected, but they often lead to the buildup of stress and strain within the crust. It's this accumulated stress that can eventually result in a sudden release of energy, which manifests as volcanic eruptions. Furthermore, within these boundary zones, the interaction of the plates often results in the formation of faults, cracks or fractures in the Earth's crust that allow the plates to move past one another. Some of these faults are relatively minor, but others are vast and capable of generating enormous amounts of energy. The San Andreas Fault in California, for instance, is one of the most famous and active fault systems in the world, stretching for over 800 miles and representing a significant boundary between the Pacific Plate and the North American Plate. It's here, along these boundaries, that volcanoes often get their explosive force, as the plates grind together, creating conditions ripe for magma to ascend toward the surface. But this process is not as simple as plates just colliding or sliding past one another. In some cases, the plates do not immediately melt into magma upon collision or subduction. Instead, enormous amounts of heat and pressure are created as the plates push against each other. This pressure can accumulate over long periods of time, gradually altering the composition of the rock and eventually leading to magma formation. As the pressure continues to build, the molten rock may eventually find its way to the surface in the form of a volcanic eruption. What's truly fascinating, however, is that the pressure from tectonic movements in one region can often influence areas far beyond the immediate vicinity. Think of it like the ripples in a pond when a stone is thrown in. A disturbance in one region, such as a tectonic plate shift near the Pacific Ocean, could very well trigger seismic activity on the opposite side of the world, eventually leading to volcanic eruptions in regions previously thought to be unrelated. This is what makes the synchronization of eruptions so intriguing to scientists. The possibility that movements deep beneath the Earth's surface could be creating a kind of global network, connecting volcanic regions through subtle shifts in the Earth's crust. Now, as the world continues to experience heightened volcanic activity, it's becoming clear that the conventional understanding of tectonic plate movements and volcanic eruptions may need to be expanded. In the past, scientists primarily focused on the immediate geological causes of eruptions, like the pressure buildup at specific plate boundaries. But we now know that these forces can resonate across the globe in ways that we hadn't fully appreciated before. In other words, eruptions are not isolated events, they may be part of a much larger, interconnected system. The question now is whether this interconnectedness is a natural part of the Earth's geological cycle, or if we are witnessing an unprecedented period of global tectonic instability. In light of these insights, researchers are now beginning to explore how specific plate movements, and even the speed at which they occur, might be contributing to the increasing frequency of eruptions. Some studies suggest that the acceleration of plate movements in certain regions could be a sign that the Earth's tectonic systems are undergoing a period of rapid change. While the plates have always been in motion, the speed and direction of that motion may be shifting, leading to an amplification of volcanic events. This idea is still very much in its infancy, but it's a topic that geologists are paying close attention to, especially as the frequency of eruptions seems to be increasing in recent years. One particularly intriguing piece of the puzzle involves the interaction between the oceanic plates and continental plates. In some areas, the oceanic plates, the denser, thinner plates beneath the ocean floor, are being forced beneath the lighter, thicker continental plates. This process, known as subduction, is particularly effective at generating volcanic activity. As the oceanic plates dive deep into the mantle, they melt and create magma, which rises to the surface in the form of volcanic eruptions. However, scientists have discovered that the angle at which the oceanic plates subduct beneath the continents can vary dramatically, which in turn affects the frequency and intensity of the eruptions. For instance, in areas where the subduction angle is steeper, the magma is able to rise more rapidly, leading to more frequent and explosive eruptions. Conversely, a shallower subduction angle can result in less frequent eruptions, as the magma is unable to reach the surface as quickly. These subtle variations in the subduction process might be part of the reason why some volcanic regions are experiencing an uptick in activity, while others remain relatively dormant. It's a delicate balance of forces that we're still trying to fully understand, but it's becoming clear that the interaction between tectonic plates is far more intricate and impactful than we ever imagined. As we continue exploring the depths of tectonic plate movements and their influence on volcanic activity, it's important to dive further into the mechanisms that drive these interactions. One of the most fascinating and crucial elements of volcanic formation is the role of magma chambers beneath the Earth's surface. These chambers are essentially vast reservoirs of molten rock that lie deep within the Earth's crust, often at the boundary zones between tectonic plates. The magma contained in these chambers is constantly under intense pressure from the weight of the rock above it, and over time, this pressure builds and builds until it reaches a breaking point. This pressure, however, isn't just caused by the tectonic plates pushing and pulling against each other. It's also heavily influenced by the rate of subduction and the type of rock involved. The rocks involved in the subduction process vary greatly in their composition, and this can dramatically alter the type of magma that forms. When an oceanic plate subducts beneath a continental plate, the oceanic plate, made mostly of basalt, begins to melt, creating basaltic magma. However, when the continental plate itself starts to melt due to the intense heat and pressure, the result is often andesitic magma, which is much more viscous and sticky compared to the fluid basaltic magma. This viscosity plays a significant role in the formation of more explosive eruptions, as the thicker magma struggles to rise to the surface, creating enormous pressure until it eventually bursts forth in a violent eruption. Another factor that contributes to the buildup of pressure within these magma chambers is the movement of fluids within the Earth's crust. Water, in particular, is a key component in the formation of magma. When oceanic plates subduct beneath continental plates, water contained within the oceanic crust is carried down into the mantle. As the plate descends, the water is released and can lower the melting point of the surrounding rock, creating magma more easily. The introduction of water can also make the magma more explosive, as the vaporization of the water causes rapid expansion when it reaches the surface, contributing to the power of the eruption. This process is most visible in what are known as arc volcanoes, which are formed at subduction zones where one tectonic plate is forced beneath another. These volcanoes tend to form in chains, as the magma that rises to the surface creates a series of eruptions along the plate boundary. The Pacific Ring of Fire, for example, is full of such arc volcanoes, as the oceanic plates of the Pacific are constantly being subducted beneath the continental plates of Asia and the Americas. These eruptions, while spectacular, also contribute to some of the most destructive volcanic events in history. But the interaction between plates and magma doesn't always result in the violent eruptions that we might associate with subduction zones. In fact, the mid-ocean ridges, the vast underwater mountain ranges that run across the ocean floor, are home to a completely different type of volcanic activity. These ridges represent divergent plate boundaries, where two tectonic plates are pulling apart rather than colliding. As the plates move away from each other, they create a gap that allows magma to rise from the mantle, filling the void and creating new oceanic crust. This type of volcanic activity is generally less explosive, as the magma is much less viscous than that found in subduction zones. However, the sheer scale of volcanic activity along these ridges, stretching for tens of thousands of miles, shows just how active and interconnected our planet's volcanic systems are. Even more intriguing is the way in which divergent boundaries also play a role in the distribution of heat beneath the Earth's surface. When tectonic plates separate, the mantle beneath them is subjected to a cooling effect, which causes some regions to become more stable and less prone to volcanic activity. However, in other areas, the separation creates conditions ripe for the upwelling of material from the deeper mantle, leading to what we call hotspot volcanic activity. Hotspots, such as the Hawaiian Islands, are regions where volcanic activity is sustained for long periods, often far from any plate boundary. These isolated eruptions occur because of a particularly hot and active part of the mantle, known as a mantle plume, which rises from deep within the Earth and creates volcanoes over the course of millions of years. Hotspot volcanism challenges the traditional view that volcanic activity is primarily confined to plate boundaries. In fact, hotspots are responsible for some of the most spectacular and long-lasting volcanic chains on Earth. The Hawaiian Islands themselves, for example, were formed by a single hotspot, and as the Pacific Plate moved across the hotspot over millions of years, a series of volcanic islands and seamounts were created. The volcanic eruptions on these islands are generally less violent than those associated with subduction zones, but the scale of activity and the way the islands have formed over time show just how dynamic and diverse volcanic processes can be. As we continue to explore the relationship between tectonic plate movements and volcanic activity, we also have to consider the role of mantle convection, the slow, churning motion of the Earth's mantle, which plays a central role in driving plate tectonics. Mantle convection is essentially a massive conveyor belt, moving material from the deep interior of the Earth to the surface and back again. This circulation of hot and cold material within the mantle is what drives the movement of tectonic plates and, by extension, the formation of volcanic hotspots and plate boundaries. When material in the mantle is heated by the Earth's core, it becomes less dense and rises toward the surface. As it cools near the surface, it becomes denser and sinks back down toward the core, where it is reheated and the cycle begins again. This process not only contributes to the movement of tectonic plates but also helps to drive volcanic activity. As the mantle material moves, it can create gaps in the crust that allow magma to rise, resulting in volcanic eruptions. The influence of mantle convection is most visible in the process of continental rifting, where large land masses like Africa and South America are slowly being pulled apart by the movement of the Earth's mantle. As the plates split and separate, magma rises to fill the gaps, forming new crust and creating volcanoes along the way. This process, which can take millions of years, is still ongoing in areas such as the East African Rift, where volcanic activity continues to shape the landscape. As we move from the forces beneath the Earth's surface, there's another crucial element to consider that significantly influences volcanic eruptions: the role of tectonic stress and the fractures it creates in the Earth's crust. It's a subtle, yet immensely powerful cause that often works behind the scenes, quietly shaping the Earth's surface over millions of years. But when it finally manifests, the results are nothing short of dramatic. Tectonic stress occurs when the forces from the movement of tectonic plates create immense pressure on the Earth's crust. This pressure doesn't always result in immediate seismic activity like earthquakes, but over time, it can lead to the development of fractures and faults in the crust. These cracks or faults can vary greatly in size, from tiny fissures to massive rifts that stretch across entire continents. When these faults reach certain critical points, they provide a pathway for magma to rise from the deeper layers of the Earth. This pathway, a vent, allows the pressure built up beneath the surface to escape, sometimes resulting in massive volcanic eruptions. A perfect example of this is what happens along transform boundaries, where two tectonic plates slide past one another. While transform faults, such as the San Andreas Fault in California, are often associated with large earthquakes, they also play a role in volcanic activity, especially when the stress from these plate movements fractures the surrounding rock. This opens up opportunities for magma to force its way through the cracks and reach the surface. When this happens, it can give rise to volcanic eruptions, which often occur in places you might not immediately associate with high volcanic activity. Imagine the pressure that builds up when tectonic plates continue their slow grind against each other over hundreds of thousands of years. Every subtle shift causes tiny cracks to form, minute fractures in the crust that, over time, grow larger. With each pressure point, the Earth's surface is slowly but surely weakened. Eventually, those cracks can create a route for magma to travel upward. The magma, still incredibly hot and under intense pressure, finds its way through these fractures, sometimes in a series of smaller eruptions, until it bursts through the surface in a violent eruption. This process isn't always quick, though. In many cases, volcanic eruptions caused by tectonic stress are the result of long, slow-building tension. Unlike the sudden pressure that can lead to catastrophic explosions, tectonic stress-driven eruptions can take years, or even centuries, to manifest. The key here is that these eruptions are more about the accumulation of stress. In some areas, the crust may become so stretched and cracked that it eventually becomes a weak point, allowing magma to force its way to the surface over time. There's also the factor of continental rifting, a process that often involves the stretching and thinning of the Earth's crust as tectonic plates pull apart. In these regions, the crust becomes increasingly fractured, and magma from deeper layers rises through these rifts, often leading to the formation of large volcanic regions. A famous example of this is the East African Rift System. Over millions of years, this rift has caused the land to fracture and pull apart, creating a massive fault zone where magma from the mantle regularly escapes, forming volcanoes along the way. In some places, these rifts are so active that entire mountain chains are built up over time, reshaped by constant volcanic eruptions. But tectonic stress doesn't just operate at plate boundaries. Intraplate volcanic activity, where eruptions happen far from plate edges, can also be influenced by tectonic stress. In these regions, the crust can be pushed and pulled by forces unrelated to direct plate movements. Stress within a single tectonic plate, sometimes from distant sources, can create fractures deep within the crust. These fractures, although not directly related to the movement of plates, can still provide conduits for magma to ascend. One of the most famous intraplate volcanic areas is the Hawaiian hotspot, where the Pacific plate moves over a stationary plume of magma from deep within the mantle, creating a chain of volcanic islands. While this isn't directly caused by the movement of tectonic plates at plate boundaries, the stress from the moving plate plays a role in how the crust thins and fractures in specific regions, allowing the magma to escape. Now, consider this idea: as the Earth's crust is stretched and compressed, it doesn't just break randomly. It does so in a manner that is both controlled and predictable. This is why certain areas of the world are more prone to volcanic eruptions than others. Volcanic hot spots, areas of concentrated activity like those found in Iceland and along the Pacific Ring of Fire, often align with these tectonic stress zones. Where stress is the greatest, whether it's from compressional forces at convergent boundaries or from the stretching forces at divergent boundaries, the potential for volcanic activity is high. Interestingly, tectonic stress also influences the type of volcanic eruptions that occur. The more brittle the crust, the more likely it is to experience explosive eruptions when magma pushes through. The more stretched or weakened the crust, the more fluid the magma will be when it escapes, leading to the formation of shield volcanoes. Shield volcanoes, with their broad, gentle slopes, tend to be the product of non-explosive eruptions, where magma flows steadily from cracks in the crust. These volcanoes, while less destructive in terms of explosive force, are still incredibly important in shaping the Earth's landscape over time. The tectonic stress theory also highlights a fascinating point. While volcanic eruptions might seem like sudden bursts of energy, they are often the culmination of long-term, slow movements beneath the Earth's surface. These eruptions are not always instant reactions to a single shift in the plates, but rather a gradual response to the immense forces at play deep within the Earth. When tectonic stress accumulates over millions of years, it changes the Earth in profound and sometimes unpredictable ways. As we move forward, it's important to recognize that volcanic eruptions are rarely caused by a single factor. In fact, the tectonic stress within the Earth's crust often works hand in hand with other geological processes like subduction, mantle plumes, and magma chamber activity. This complex web of interconnected forces makes it clear that volcanic eruptions are not just random explosions. They are part of a much larger and intricate geological system. Each factor feeds into the next, creating the conditions necessary for the powerful eruptions that continue to shape the Earth's surface. As we venture further into the realms of possibility, let's leave behind the well-established mechanisms of tectonic plate movements and delve into a theory that feels more like something from a science fiction novel: interplanetary and cosmic forces influencing volcanic eruptions. At first glance, this might seem like an idea pulled from a space fantasy, but bear with me, because the more we learn about our planet and the universe, the more we realize that Earth is not an isolated system. The vastness of space, with its gravitational forces and cosmic phenomena, could very well be influencing the behavior of our planet's geological processes in ways we haven't yet fully grasped. It's not as far-fetched as it might sound, and in fact, some scientists are beginning to entertain the idea that celestial forces might be playing a much larger role in volcanic activity than we previously thought. Let's start with the idea of planetary alignments. For centuries, human civilization has been fascinated by the movements of the planets, and the ancient astronomers were often quick to ascribe meaning to these alignments, interpreting them as signs of great changes or disruptions. While we've long moved past superstition, there's a scientific theory that suggests these alignments might actually exert a measurable influence on Earth's geology. Imagine this: the massive gravitational forces exerted by planets like Jupiter, Saturn, and even Mars, when they align in particular ways, might have an impact on Earth's tectonic plates. Now, Jupiter, for example, is a behemoth of a planet, with a gravitational field so powerful that it can sway the orbits of asteroids, moons, and even distant comets. So, it's not unreasonable to think that when Jupiter is in alignment with Earth, its gravitational pull might cause subtle shifts in the Earth's crust. These shifts wouldn't necessarily be large enough to cause massive earthquakes or volcanic eruptions on their own, but they could provide just the right amount of added pressure or stress to already volatile regions of the Earth. Regions that are on the brink of tectonic movement might experience just enough of a nudge, enough of a push, for that dormant volcano to erupt, or for a fault line to slip. There's an even more intriguing idea that emerges when we look at gravitational stress. It's not just the obvious forces at play when planets align, it's the subtle, almost imperceptible changes that these alignments can introduce to the Earth. Some scientists speculate that when planets like Jupiter and Saturn align, their gravitational pull could induce a form of stress on Earth's crust, especially in the molten layers beneath the surface. This stress might be enough to influence the flow of magma beneath the Earth's surface, triggering volcanic activity in places we might not expect. Think about it. Volcanic eruptions often occur in areas where the pressure from the Earth's mantle exceeds the structural integrity of the crust. What if these gravitational forces from far-off planets help tip the balance in just the right moment, nudging the Earth's crust into a fracture? But planetary alignment isn't the only cosmic factor to consider. Solar activity, particularly the unpredictable bursts of energy from the sun, may also play a part in triggering volcanic eruptions. When the Sun experiences a particularly powerful flare or releases a coronal mass ejection, CME, it sends out a surge of charged particles into space. These particles can interact with Earth's magnetosphere, potentially causing disruptions in the Earth's electromagnetic field. The magnetic field is more than just a protective shield. It's a dynamic system that interacts with the Earth's interior. Could the intense energy from a solar flare have a cascading effect on the molten core of the Earth? When this energy interacts with Earth's magnetic field, some scientists propose that it could induce electromagnetic currents deep within the Earth's crust. These currents might not be something we can directly measure with our current technology, but it's possible that they could influence the behavior of magma beneath the surface. Imagine the flow of magma being subtly altered by these solar-induced currents, shifting it in ways that increase pressure on tectonic plates or create new channels for magma to escape. As pressure builds up, a volcanic eruption could be the inevitable result. The idea that solar activity could influence volcanic eruptions may sound like a stretch, but there's a compelling argument for the interconnectedness of all the forces in our solar system. The Sun's energy doesn't just affect our atmosphere, it could be subtly interacting with the Earth's inner workings as well. Now, let's push the boundaries of imagination a bit further and consider the influence of cosmic rays, those high-energy particles that travel through space from distant stars and galaxies. Cosmic rays have been shown to interact with Earth's atmosphere, and some researchers believe they might even play a role in influencing the planet's geological systems. These rays are incredibly energetic, and while we're used to thinking of them as a hazard to our space missions or communication systems, could they also have an effect on Earth's tectonic processes? Some scientists suggest that the interaction between cosmic rays and Earth's atmosphere could have an indirect effect on the Earth's crust. For example, cosmic rays might alter the composition of certain minerals within the mantle, potentially making them more susceptible to melting. If this is the case, the influence of cosmic rays might be a contributing factor to the process of mantle convection, where heat from the core rises toward the surface, eventually creating volcanic hotspots. Again, this is an area that is still far from conclusive, but it's an intriguing theory that opens up the possibility that forces from beyond our planet could be involved in volcanic activity in ways we have yet to fully comprehend. In this new light, we begin to see that Earth's volcanoes might not just be a product of local geological conditions, but a result of a much broader cosmic dance. The forces of gravity, solar activity, and cosmic rays might all play their part in influencing the pressure and stress within the Earth's crust, triggering eruptions when conditions are just right. It's a humbling reminder of how interconnected everything is in the universe, with forces far beyond our control or comprehension quietly shaping the world we live in. These cosmic phenomena, seemingly distant and detached, might have more power over our planet than we ever imagined. In the end, while the idea that cosmic forces could trigger volcanic eruptions is still speculative, it presents a fascinating perspective. Perhaps, just maybe, the next great eruption won't be solely the result of tectonic movements, but the culmination of celestial forces reaching out from across the galaxy, subtly influencing the molten heart of our planet in ways we are only beginning to understand. This cosmic connection between the stars, the planets, and the Earth is a mystery still waiting to be unraveled. Let's explore the potential consequences and effects that could arise if multiple volcanoes were to erupt in sync. This scenario, while still a bit speculative, raises the intriguing question: what if the Earth's volcanic systems were not isolated, but rather in some way interconnected, to the point where simultaneous eruptions could create a global cascade of catastrophic events? Imagine, for a moment, that multiple volcanoes around the world begin to erupt almost simultaneously. The initial thought might be that we're simply witnessing isolated eruptions, each with its localized impact on nearby communities. However, if this were to happen on a global scale, the implications could extend far beyond the local region. Let's start by considering the atmospheric effects of multiple volcanic eruptions. When a volcano erupts, it doesn't just spew lava. The explosive force often propels huge amounts of ash, sulfur dioxide, and other gases into the stratosphere. These particles can stay suspended in the atmosphere for months, or even years, depending on the scale of the eruption. If several volcanoes were erupting simultaneously, the sheer volume of ash and gas injected into the atmosphere would increase exponentially. This could lead to a phenomenon known as a volcanic winter, a dramatic drop in global temperatures. The sulfur dioxide and ash particles released into the atmosphere have a cooling effect on the planet, as they block sunlight from reaching the Earth's surface. Historically, we've seen this after major volcanic events. For example, the eruption of Mount Tambora in 1815 led to what was known as the Year Without a Summer, where temperatures dropped drastically, crops failed, and famines spread across parts of the world. Now, imagine the compounded effects of several major eruptions happening at once, not just in one part of the world, but across continents. The cooling effect could be much more severe, and it wouldn't just impact the regions closest to the eruptions, it would be felt globally. With the global temperature dropping, the agriculture industry would face immediate and severe challenges. Shortened growing seasons, cooler temperatures, and the potential loss of crops could lead to widespread food shortages. Farmers around the world would struggle to grow the necessary amount of food to feed the population, leading to a significant economic crisis. Prices for basic food staples would rise dramatically, creating instability in food markets and increasing the risk of famine. Countries that rely heavily on agricultural exports would suffer major economic losses, while nations that depend on imports for food would experience extreme food insecurity. The cooling of the planet's surface would also have an impact on the global climate system. Shifts in weather patterns could become more erratic. Some areas might experience heavier rainfall and flooding, while others may face prolonged droughts. A disruption in the global climate would affect everything from freshwater availability to the migratory patterns of animals. These changes in weather would make it difficult to predict and prepare for natural disasters, compounding the challenges people would face in an already tense environment. The very delicate balance of ecosystems could be thrown into chaos, affecting both wildlife and human populations. Beyond the immediate environmental effects, the economic consequences of synchronized volcanic eruptions would be catastrophic. Industries that rely on stable weather patterns, such as agriculture, fishing, and tourism, would be hit hardest. The global economy could grind to a halt as governments and companies scramble to adapt to the sudden and dramatic changes in climate. Power grids might fail as disruptions to the environment cause widespread infrastructure damage. In regions already dealing with political or economic instability, the added stress could lead to conflicts over resources, exacerbating tensions and creating global unrest. On a societal level, the human toll of such an event would be staggering. The direct impacts of volcanic eruptions, such as lava flows, pyroclastic flows, and ashfall, would devastate entire communities near the volcanoes. But the larger effects of global cooling, crop failures, and economic collapse could lead to widespread famine, disease, and displacement. As resources become scarcer and the world's population grows more desperate, the risk of civil unrest increases. Entire cities might see mass migrations as people flee from areas hit hardest by the cooling effects, looking for more habitable land. One of the most profound effects could be on public health. Volcanic ash, while a direct hazard to those living near an erupting volcano, could have a more insidious long-term impact. The widespread ashfall could contaminate water supplies, destroy crops, and severely limit access to fresh air. People in affected areas might experience respiratory problems, and the stress of living in such harsh conditions could exacerbate existing health issues. The medical infrastructure in many regions might already be stretched thin due to the effects of the eruptions themselves, but the additional strain of managing a global health crisis could lead to widespread suffering. Another issue to consider would be the potential for environmental degradation on a massive scale. The eruption of multiple volcanoes simultaneously could also result in the release of large amounts of toxic gases such as carbon dioxide, sulfur dioxide, and hydrogen sulfide. These gases would not only contribute to the global cooling but could also acidify oceans, lakes, and rivers. Marine life, already vulnerable due to changes in water temperature and chemistry, could face even greater challenges. A sudden influx of acid into aquatic ecosystems could decimate fish populations and disrupt the balance of entire oceanic food chains. In a world already facing the challenges of climate change and pollution, the added strain of volcanic gases would accelerate the deterioration of biodiversity. So, when we think about the consequences of multiple volcanoes erupting in sync, we aren't just talking about localized destruction. We're talking about a global disruption, one that could send shockwaves through every aspect of life on Earth. From the climate to the economy to human survival, the cascading effects of such an event would be felt on a scale that we can barely comprehend. And while this may seem like an extreme or even fantastical scenario, it serves as a stark reminder of how interconnected our planet's systems truly are, and how a chain of seemingly isolated events could spiral out of control, reshaping the world as we know it. As the world grapples with the terrifying prospect of multiple volcanoes erupting in sync, both scientists and governments would undoubtedly spring into action to assess the situation and attempt to mitigate the catastrophic consequences. The urgency and complexity of such a scenario would require unprecedented coordination and innovation. In this ever-evolving crisis, what could these key players do to respond to such a massive global challenge? Let's begin by examining the role of scientists in this crisis. They would be on the front lines, tasked with understanding the volcanic activity and predicting the extent of the eruptions. The first priority would be monitoring. Scientists would need to track the seismic activity leading up to the eruptions, using satellites, ground sensors, and deep-sea observatories to get real-time data on volcanoes worldwide. With eruptions happening in sync, the idea of a global volcanic system would need to be investigated thoroughly. This could lead to the development of new predictive models that take into account the possibility of widespread eruptions. While volcanic activity is often studied individually, scientists would likely need to rethink how these volcanoes could be interconnected in new and complex ways. Advanced algorithms and AI tools would play a crucial role in processing this data, helping to predict when and where the eruptions are likely to intensify. In the early stages, volcanic warning systems would be put into place, with scientists warning the global population about the potential for dangerous ash clouds, lava flows, and pyroclastic surges. They would also work tirelessly to predict the environmental consequences, from the cooling effects on the climate to the anticipated spread of volcanic gases like sulfur dioxide. Given the scope of the disaster, it's likely that international collaborations would emerge, as scientists from various nations would share information and resources to track the eruptions. The focus would be on real-time global monitoring, perhaps involving satellites positioned in space, providing live footage of volcanic activity, as well as offering constant data on atmospheric composition and temperature shifts. This information could then be relayed to governments and the public, helping them prepare for the worst-case scenario. One of the key concerns for scientists would be predicting the long-term effects of these eruptions. They'd be deeply concerned with the trajectory of the ash clouds, which could encircle the globe, leading to what's known as global dimming. Scientists would collaborate on complex climate models to simulate the consequences of reduced sunlight and cooling temperatures. They would attempt to predict the impact on agriculture, water sources, and ecosystems, synthesizing this data to give governments a clear picture of the extent of the damage. They'd also need to advise on the potential health risks from ash inhalation and how widespread respiratory issues could become as volcanic debris settles across vast regions. On the other side of the equation, governments would have to act swiftly and decisively to respond to the crisis. The first step would undoubtedly be evacuations. Governments would need to mobilize large-scale evacuation efforts to protect citizens living near the volcanoes. These evacuations would be chaotic, as entire regions would need to be cleared to avoid the immediate danger posed by lava flows and ash clouds. Given the global nature of the threat, it would be impossible for any one nation to address the crisis alone. Instead, we would likely see unprecedented international cooperation, with nations coming together to share resources, expertise, and supplies. Emergency funds would be deployed to aid in the evacuation efforts, provide shelter, and ensure the continued safety of affected populations. As the eruptions unfold, relief efforts would shift focus to immediate survival. Governments would likely set up emergency shelters to house displaced populations, with relief teams providing food, water, and medical supplies. However, as volcanic ash and gases begin to cover vast expanses of land, reaching areas far from the eruption sites, the logistical challenges would intensify. Governments would need to coordinate the delivery of resources to areas that are cut off from major roads and airports, using planes, helicopters, and boats to ensure survival supplies get to the most affected regions. Food and water scarcity would become a real concern, as infrastructure is severely impacted. Governments would need to prioritize the distribution of these essential resources while trying to keep order during times of panic and uncertainty. The next major challenge governments would face is the economic fallout from these eruptions. With global temperatures dropping, leading to widespread crop failures, governments would need to figure out how to secure food for populations already suffering from shortages. This would likely involve large-scale importation of food supplies, and governments would also begin looking into ways to stabilize the global economy, particularly in industries like agriculture, fishing, and energy that would bear the brunt of the crisis. Governments might even resort to rationing certain resources to prevent hoarding and ensure that everyone has access to essential items. At the same time, global trade would be disrupted, and countries with strong economic power could come under pressure to support the most vulnerable nations. This would undoubtedly be a major point of tension in international relations, as countries work to balance domestic needs with global solidarity. While immediate concerns about survival would be the focus, governments would also have to plan for the long-term recovery. The potential for a global cooling effect means that governments would need to prepare for years of colder temperatures, altered weather patterns, and potentially even a mini ice age that could devastate agriculture for generations. This would lead to a push for renewable energy solutions as governments would need to rethink their energy strategies in response to these shifting climate conditions. With traditional energy sources, such as coal and natural gas, becoming more difficult to rely on due to global disruptions, investments in alternative energy would take center stage as governments strive to rebuild a more sustainable and resilient energy infrastructure. As governments and scientists work together, the need for global diplomacy would be paramount. The cooperation between countries would likely be tested in unprecedented ways, as leaders navigate the political, social, and economic turmoil created by simultaneous volcanic eruptions. Countries with more resources might feel the pressure to help less developed nations, while at the same time dealing with their own crises. This global disaster could either bring humanity closer together in cooperation, or further entrench existing divisions. In response to all of these challenges, governments would also likely begin investing in new technologies to better prepare for future volcanic events. For instance, enhanced satellite systems could be developed to monitor volcanic activity in real time, providing earlier warnings and more detailed predictions. International efforts would also focus on developing climate modification strategies that could counteract the cooling effects of volcanic eruptions, potentially through geoengineering projects like injecting aerosols into the atmosphere to reflect sunlight, or creating artificial clouds to stabilize temperatures. As we bring this exploration to a close, it's clear that the idea of multiple volcanoes erupting in sync is a terrifying yet fascinating scenario that challenges both our understanding of the Earth and our ability to respond to global crises. From the potential causes to the far-reaching consequences, every aspect of this issue paints a picture of a world thrown into chaos. But through that chaos, there is also hope, the hope that our collective efforts, from scientific advancements to international cooperation, could guide us through the storm. Let's take a moment to reflect on the possible causes that could spark such a dramatic chain of events. The idea of synchronized volcanic eruptions, once thought to be nearly impossible, becomes more plausible when considering both the natural and artificial forces that could trigger them. Subduction zones, where tectonic plates converge and generate immense pressure, are certainly a primary candidate. These zones, scattered around the globe, could experience a surge in activity, causing volcanic eruptions to follow a pattern of interconnectedness. However, beyond the natural world, more extraterrestrial forces could come into play. The hypothetical influence of a rare cosmic event, like a massive solar flare or the sudden gravitational pull of a passing celestial body, might be the unseen trigger behind a synchronized volcanic explosion. This brings an entirely new level of complexity to the situation, blending scientific theory with a touch of speculative thinking. Whether it's the deep tectonic pressures beneath the Earth's crust or the cosmic forces beyond our comprehension, the causes of such a phenomenon are as mysterious as they are extraordinary. As we consider these causes, it's impossible not to focus on the devastating consequences that would unfold should these volcanoes erupt simultaneously. The immediate threat to human life and infrastructure is undeniable. Lava flows, pyroclastic surges, and massive ash clouds would engulf entire regions, displacing millions of people and leaving entire cities uninhabitable. The disruption to air travel, agriculture, and global trade would be immediate and catastrophic. Yet, it's the long-term effects that truly set the scale of this disaster apart. The potential for a dramatic global cooling effect caused by the massive amounts of ash and gases released into the atmosphere could lead to widespread agricultural failure, food shortages, and even societal collapse. What we often overlook is the ripple effect of such an event, not just the immediate threat to life but the cascading consequences that follow. Our global economy, our climate, and the very fabric of our societies would be tested in ways we have never experienced before. Yet, in the face of this overwhelming threat, we find that science and governments are not sitting idly by. They are already exploring ways to mitigate the damage and reduce the impact of volcanic activity on the planet. Scientists are using cutting-edge technologies to monitor volcanic activity in real time, develop early warning systems, and model the effects of such eruptions on the global climate. They are studying the possibility of interconnections between volcanoes, seeking patterns that could predict the next eruption before it happens. Governments, meanwhile, are preparing for the worst, organizing large-scale evacuations, and coordinating relief efforts to ensure that people in affected regions have access to food, water, and medical supplies. While no response could ever fully prepare us for the scale of such a disaster, the efforts being made today are laying the groundwork for better handling potential crises in the future. As we consider the long-term recovery from such an event, it becomes clear that our survival would depend on global cooperation. The resources of individual nations would likely be stretched thin, but it is through collaboration on an international scale that we could begin to rebuild. Sharing knowledge, technology, and resources would become critical in ensuring that the most affected regions receive the aid they desperately need. Furthermore, as governments face the reality of a cooler climate and its effect on agriculture, energy, and global trade, the push for renewable energy and climate adaptation strategies will become more urgent than ever before. The response would not only be about managing the crisis in the immediate aftermath, but about ensuring humanity's resilience and long-term survival in the face of climate changes that we can scarcely predict. In the end, while the idea of multiple volcanoes erupting in sync may seem like a nightmare, it serves as a reminder of just how interconnected our world is. The Earth is constantly shifting beneath our feet, influenced by forces both natural and cosmic, and our preparedness for the unpredictable will ultimately determine how we fare in the face of such challenges. The causes we've discussed, from tectonic movements to cosmic events, highlight the delicate balance of forces that shape our planet, while the potential effects emphasize the vulnerability of our global systems. But through science, innovation, and cooperation there is hope. We may not be able to stop the eruption of a volcano, but with the right knowledge, resources, and solidarity, we can rise to meet the challenges ahead. The future remains uncertain, and this scenario, though seemingly extreme, serves as a powerful reminder of the potential threats that could arise on a global scale. But it also serves as a call to action, an invitation for governments, scientists, and citizens alike to remain vigilant and prepared for whatever the Earth may throw our way. With foresight, planning, and a commitment to working together, we can weather the storm, no matter how powerful it may be. Before we wrap up, if you found this deep dive into the potential chaos of synchronized volcanic eruptions as fascinating as we did, don't forget to like this video and subscribe to the channel. Stay tuned as we continue to explore the forces of nature and the mysteries of our planet. By subscribing, you'll be joining us on this incredible journey, always staying one step ahead and understanding the world around us. We appreciate your support, thank you for watching, and we look forward to diving into more mind-blowing topics with you soon.